All right, let's jump right into this explainer. Today, we've got something incredibly exciting for anyone tracking the bleeding edge of large language model efficiency. We're looking directly at a freshly launched GitHub repository from DeepSeek AI called DeepSpec. Look, if you've been working with AI optimization, you already know how absolutely crucial it is to speed up model inference. Well, that's exactly what this project tackles head-on. We're going to break down this entire repository step by step, so you can see exactly how to leverage this code base for your own projects. And right off the bat, you can see the massive impact this release is having. The repository has already accumulated 693 GitHub stars and 48 forks. That kind of rapid momentum tells us one thing for sure. Developers are hungry for a standardized, reliable toolset in this highly specific domain of AI optimization, and DeepSeek AI has totally delivered.
So what exactly is it? Well, to use their exact phrasing, DeepSpec is a full-stack code base for training and evaluating draft models for speculative decoding. We don't need to get bogged down in the complex math of speculative decoding itself today, but basically it's like a tag team speed hack, where a tiny model drafts answers fast and a huge model double-checks them. The real key word here is full stack. This isn't just a disconnected script or a white paper, it's a complete, end-to-end environment handling everything from initial data prep all the way to final model evaluation.
To make this super digestible, we'll follow the exact sequential pipeline of a developer would experience. Our sections are 1. Introduction 2. Data preparation 3. Model training 4. Evaluation and finally, 5. Algorithms and open source.
Section 1. Introduction. Repository makeup. Okay, let's dive into this technical foundation.
I always love looking at the language breakdown first because it tells you immediately what you're dealing with. As you can see, the codebase is overwhelmingly Python, 97.9%, with just a tiny sliver of shell scripts at 2.1%. This means setting up your environment is refreshingly simple. You essentially just need to install the provided Python dependencies and you're good to go. No multi-language compilation nightmares here.
That simplicity extends directly into the workflow itself. It's a strict 3-step sequential process: data preparation, training, and evaluation. It's a completely linear pipeline where each stage's output feeds directly into the next. You build the foundation, you train the model, and then you evaluate it.
Section 2. Data preparation. Building the cache. Now, what's really interesting about this next stage is the sheer amount of heavy lifting required before any training even happens.
Let's walk through the active, step-by-step data pipeline. First up, you download and split the training data. Pretty standard practice. But step 2 is where it gets highly specialized: regenerating target answers. Your tiny draft model needs a massive amount of correct output from a larger target model to learn from. So you'll actually need an active inference engine running to serve that target model while you regenerate these answers. Finally, step 3 is preparing all that freshly generated data into what they call the target cache.
Now brace yourself for this next number. 38. That's 38 terabytes of storage required just to hold the target cache for the default QN or QN34B setting. To put that into perspective, you can say goodbye to your local laptop SSD. You need serious enterprise-grade storage infrastructure prepared before you even think about starting this pipeline.
Section 3. Model training. Launching the workers. This is where we actually train a draft model against those cached target outputs we just built. The mechanics here are actually elegantly simple. You execute a shell script, train.sh, which in turn launches train.py. What's really vital to understand is how it handles resources. It automatically spawns exactly one worker for every single visible GPU in your system, and as it trains, it seamlessly writes your checkpoints into a designated folder, organized neatly by project, experiment, and step number.
Speaking of GPUs, the repository has certain hardware assumptions baked in, and the number 8 is key here. The default hardware configs and scripts assume you're operating on a single node equipped with 8 GPUs. If you're running with fewer than 8, you've got to remember to manually reduce your CUDA visible devices environment variable, otherwise the scripts will literally crash trying to find hardware that just isn't there.
So the crucial point is how you actually configure these runs, because flexibility is totally built in. You have 2 main levers to pull. The primary method is pointing your config path at a pre-built configuration file to select your algorithm and model. But let's say you just want to tweak one minor detail. Instead of writing a whole new file, you can just use the -ops command line argument to override specific configuration fields on the fly. It's a really nice balance of structure and runtime flexibility.
Section 4. Evaluation. Measuring acceptance. Here is where we measure the actual speculative decoding acceptance rates.
Just like the training phase, evaluation is driven by a straightforward shell script. Eval.sh runs eval.py. But to make this work, you must provide the script with two critical paths: the path to the original target model and the path to your newly trained draft checkpoint. It absolutely needs both to compare the performance accurately.
And this brilliantly illustrates how rigorous the testing is. You aren't just running one simple check. You are hitting math-heavy benchmarks like GSM 8K and AME 25, grueling coding gauntlets like Human Evil and MBPP, and general instruction following tests like MT-Bench and Alpaca. The repository forces you to comprehensively prove your model works across a huge variety of scenarios.
Section 5. Algorithms and Open Source. The Community Foundation. Let's move to and see how this builds upon the broader AI ecosystem.
Right out of the box, DeepSpec comes loaded with 3 primary draft model algorithms: DSpark, DFlash, and Eagle 3. You don't have to code these from scratch. They're fully integrated and ready to be selected in your config files from day one.
I really love how transparent the authors are about their collaborative ethos. They explicitly state, DeepSpec builds on the ideas and code of several excellent open source projects. And to keep that momentum going, the entire repository is released under the MIT license, meaning you have immense freedom to use, modify, and distribute this codebase however you see fit.
They back up that collaborative spirit with meticulous attribution. Just look at this table. It breaks down exactly whose shoulders DeepSpec is standing on. The training framework and Eagle 3 implementation are adapted from SpecForge. The draft model design comes from DFlash, and the target model families they support are built around QN3 and Gemma. It's just a fantastic example of a full-stack solution intelligently aggregating the best open-source tools available.
Which leaves us with one final, exciting thought. The authors explicitly welcome contributions for new algorithms. They've built the pipeline, structured the massive data handling, and set up the rigorous evaluation benchmarks. The entire infrastructure is right there waiting. So the real question is, what algorithm will you contribute? Thanks for joining me for this explainer, and I highly encourage you to go check out the DeepSpec repository for yourself.